Good afternoon, Professor David de los Reyes. My topic today or this afternoon will be another variation in the computation of volume under integral calculus. I have finished already circular disk method, so I will discuss this afternoon the so-called hollow cylinder method concepts on how to compute volume under integral calculus. Okay, lesson number 68 under my channel, under the topic integral calculus, volumes, hollow cylinder method concepts. It's been my style that if I will give you a problem, I will discuss first the concepts, so you will not get lost when we are solving the problem. The very important thing is always the theory, the concept. Okay, let's bring out the concept. I will try to draw a function of x on the rectangular coordinate system. Y-axis, x-axis, this should be the curve. I designate that curve to be y equal to a function of x. Okay. I got a lower limit, I got a vertical line x equal to a, x equal to b. The problem here is that if I will try to rotate the area between x equal to a and x equal to b, this total area here, if I will try to rotate that one complete revolution, okay, what will happen? What will happen will be something like this. You create a hollow cylinder, okay, a hollow cylinder with a certain thickness. Okay, it got a thickness. If I will try to rotate the area between x equal to a and x equal to b, one complete revolution, okay, you will create a hollow cylinder. It is something like this. The thickness, it got a certain thickness. And for this representation here, the thickness is actually dx. For the meantime, we are discussing case 1. If the hollow cylinder is to be rotated with respect to the y-axis, okay, with respect to the vertical line. Okay. So to bring out the formula on how to take the volume of that one, okay, we will draw first a differential area. This is the differential area. This point here is y higher, this is y lower, the thickness is dx, and the radius of the cylinder with respect to the y-axis is designated by r. And for case number 1, this should be x. Okay? We rotate this differential area, so its distance from the axis of rotation is actually r, and that is equal to x. Okay? dB form when differential area is rotated, it is something like this, guys. Okay? If we rotate this differential area one complete revolution, what will come out will be a hollow cylinder. So our topic is actually hollow cylinder method. It's hollow. Later on, the resulting volume will not be hollow because as we integrate, we will place a limit, so it will become a solid thing, you know. But for the meantime, it is a hollow cylinder method. But once we substitute the upper and lower limit, it will become a solid. Okay? The radius of the hollow cylinder is r, and it is designated by x. That is for case number 1. If it is rotated with respect to the y-axis. This is the height. This is the variable height. It's variable because the graph is not a straight line, okay? It's going up. So as this differential area moves from x equal to a, x equal to b, this height is actually varying, okay? So the height is actually y higher minus y lower. This variable height is actually the y at this point here minus the y at this point, and that is the altitude. And the radius with respect to the axis of rotation is r equal to x. Okay? Yx, it is an abscissa. It is measured along the x-axis downward vertically. Okay? Let's unwind this area here to compute for the volume, so we could visualize it. We cut this one at the middle when we try to spread out. As we spread out, the resulting figure will be something like this. Unwind layer of differential area. We cut it here, then we try to spread out. So actually, this total length is actually the circumference, right? And we know that circumference is actually 2 pi r, right? The thickness is dx. That is for case number 1. If the hollow cylinder is to be rotated with respect to the x-axis, y-axis rather, the thickness should be dx. This is h, and this is designated by y higher minus y lower. Okay. Therefore, differential volume now, it's easy, guys. It seems for the meantime it is a rectangle. So take for the volume of this, take the length, this length here, multiplied by this height here, okay, that's area. Multiplied by the thickness, that will now be volume. So I place it here, differential volume is circumference times thickness times height. Unit length times unit length times unit length, it should be a cubic unit, okay? And that is actually volume. Okay? For case number 1, if the hollow cylinder is to be rotated with respect to the y-axis, okay, the radius will be x, the thickness will be dx, and the height will be y higher minus y lower, in which y higher is given on the problem to be a function of x. It could take any function, whatever will be the function, right? And y lower will be g of x. This g of x, it could be 0 or it could be a complicated equation. Okay? Because under the circular disk method, this y lower is actually 0. But for the hollow cylinder method, there come a time that it will be 0, and there could be a time that it will be a complicated equation. So be very ready for that situation when that occurs, okay? So for case number 1, differential volume will be 2 pi x times the quantity, I write the equivalent of h first. So this is y higher minus y lower times dx. So this is actually the differential equation for taking the volume if the hollow cylinder is to be rotated with respect to the y-axis. Supposing this hollow cylinder, we configure it to be lying down along the x-axis, something like that, and it will be rotated along the x-axis. Okay, this will be the case. This will be the formula. This will be 2 pi, instead of x, it should be y, and the variable height should be xr minus xl, and the thickness should be dy. So that's case number 2. If the hollow cylinder is to be rotated along the x-axis. The first case is actually rotated along the y-axis. For case number 2, this should be the configuration. Same as this, except that the length will be 2 pi r, and they should be 2 pi r or simply 2 pi y. And the thickness is dy, and the height, instead of y higher minus y lower, since this is to be rotated with respect to the x-axis, it should be xr minus xl. Okay? So there are only 2 variations. So to bring out a formula on how to take the volume, if it is rotated with respect to the y-axis, this will be the formula. If it is rotated with respect to the x-axis, this should be the formula. Why am I discussing this one? Concepts, guys. Before we go with the application, we should know the theory and how to compute for volume. You cannot just go to problems without knowing concepts. Okay, it's always concepts. Like in integral calculus, we pass by all the integration methods before we go with the application. So whatever will be the integration that is needed, just apply it. Like in here, why am I discussing concepts? Because when we go to the application problem, we should know this concept. Okay. Good afternoon, Los Angeles.